For years now, there's been this quiet crisis brewing in cosmology. It's a really deep disagreement that suggests something we think is fundamental, about the very fabric of space-time itself, might just be totally wrong. And listen, this isn't some tiny rounding error. As one paper puts it, just bluntly, something is wrong with our measurements, or something is wrong with our model, or both. We've got a genuine cosmic whodunit on our hands, and the clues are pointing in completely different directions. Okay, so here's the heart of the problem. We have two, gold standard ways of measuring how fast the universe is expanding. When we look at the universe's baby picture, the leftover light from the Big Bang, we get one number, about 67.4. But when we look at the adult universe, the stars and galaxies around us today, we get a totally different number, 73. And this gap, what we call the Hubble tension, it's not getting smaller as we get better data, it's actually getting bigger. And if that wasn't enough of a headache, there's another problem. And it's related. Our best models, they predict that all the matter out there should be in this huge, lumpy network called the cosmic web. But when we actually go and look, the universe is, well, it's smoother than it should be. It's less structured. It's just not clumping together the way our theories say it should. So what in the world is going on? Why are we getting these conflicting answers? Well, it seems to come down to when and where we're looking. It's like we have two perfect watches, started at the exact same time, but right now they're telling us two completely different stories. So our early universe measurement comes from the cosmic microwave background, the CMB. It's basically the universe's baby photo, when everything was incredibly young and simple. We take that photo, run it through our standard model, and predict what things should look like today. Our late universe measurement, on the other hand, uses exploding stars, supernovae, as these amazing cosmic yardsticks to measure distances right here, right now. Two different methods, two different times, and two results that just refuse to agree. But this is where the plot really thickens. I mean, if the problem is just early versus late, then how come some other measurements we make in the modern universe actually agree with the old number? This is a really crucial piece of the puzzle. The answer has this wild name, baryon acoustic oscillations, or BAO. The easiest way to think about it is as a fossilized ruler. You see, BAO isn't actually measuring the expansion rate of today. It's using a set distance that got kind of frozen or imprinted onto the fabric of space way back when the universe was a baby. So of course it agrees with the early universe data. It's basically using an ancient ruler to measure things today. And all of this leads us to a pretty radical idea. An idea that might just solve both of these mysteries at once. And it starts by questioning one of the most basic things we thought we knew about the cosmos. For decades, all our models have been built on one simple foundation. If you zoom out far enough, the universe is expanding at the same speed everywhere in every direction, a universal constant. But what if it isn't? What if the Hubble constant isn't actually constant at all? This is the core of the new theory, differential expansion. It suggests that space itself stretches faster in the giant empty voids between galaxies and expands slower where all the matter is bunched up, inside those dense filaments of the cosmic web. Now, the first thing you're probably thinking is, wait a second, does this just mean we live in a weirdly empty patch of space, a local hole that's throwing off our measurements? And that's a great question. And the answer is a firm no. This isn't about our neighborhood being special, it's a property of the whole universe. Think of the cosmos as a giant block of Swiss cheese. The cheese parts, that's where the galaxies are, and that's expanding slowly. The holes, those are the voids, and they're expanding super fast. And here's the kicker, the holes take up most of the space. So no matter where you are, when you look out, your line of sight is going to go through a bunch of those fast expanding holes, giving you a faster average speed. So that's the big idea. But how does this one concept, differential expansion, actually solve the two huge problems we started with? Let's connect the dots, because this is where it gets really cool. So let's rewind. Remember that baby picture of the universe, the CMB? It was almost perfectly smooth, a simple system. The relationship between time and expansion was simple, and it was the same everywhere. But the universe today, it's had 13 billion years to get clumpy and complex and form that cosmic Swiss cheese structure. The simple old relationship between time and expansion, it's evolved. The rules have changed because the universe has changed. And here's how it cracks the case. That Hubble tension, that 8% difference, It's not an error. It's the real physical difference that is built up over billions of years as light travels through this complicated, lumpy space. And the clumpiness problem? Well, that faster expansion in the voids is actively fighting against gravity, pulling structures apart. That makes it harder for things to clump together, which makes the universe look less lumpy than our old models predicted. One elegant idea. Two mysteries solved. But wait a minute. If space is expanding differently all over the place, doesn't that mess with the supernovae? Doesn't that mean our standard candles aren't so standard anymore? Well, no. And this is a really critical point. The theory says the problem isn't with the source of the light. The star explodes the same way no matter what. The weirdness happens on the light's journey to us as it travels through that Swiss cheese cosmos. In other words, the candle is fine. It's the ruler that's gotten all warped and stretchy. Look, a cool idea is one thing, but this is science. For this to be taken seriously, it has to make predictions we can actually go out and test. It has to give us a way to prove it's wrong. And this one does. It predicts that our measurements should totally depend on what we're looking through. A supernova seen through a dense galaxy cluster should give a different expansion rate than one seen through a giant void. It predicts that these tensions should get smaller the further back in time we look. And finally, it predicts that the two tensions, Hubble and clumpiness, should actually be connected. They should show up in the same parts of the sky. And what's so great is that we can test this right now with data we already have. The experiment is actually pretty straightforward. Take our best list of supernovae, map the path the light from each one traveled to get here, and then give that path a void score based on how much empty space it crossed. If the theory is right, the supernovae with the highest void scores will also have the highest expansion rates. If there's no connection, well, the idea is wrong. It's a clean make-or-break test. Which brings us to a final thought. For nearly a century, the Hubble constant has been a pillar of cosmology. If it turns out it's not a constant at all, but just an average of a much more complex, messy reality, well, it really makes you wonder, doesn't it? What other fundamental rules of the cosmos have we just been taking for granted, waiting to be discovered in the cracks of our own data?